all decision variables that we've seen so far are restricted to have the value of greater than or equal to 0, right? That's why you always write down in the sign restriction part that all variables is greater than or equals to 0. However, in some problems, when you formulate the problem, sometimes there are variables that may be unrestricted in sign. Unrestricted in sign means that the sign of the value of that variable may be negative, may be positive, may be 0. So it may take any real value in a real number. That's why it is called unrestricted in sign. Now in this video and the next one, we are going to see how we may handle those kind of variables such that we may still solve the problem using simplex algorithm that we've learned before. So let's start. So in simplex method, if the BFS is not optimal, we will pick an entering variable and then we will try to make the value of that entering variable as large as possible. But at the same time, we need to pick a leaving variable such that when we put the value of entering variable as large as possible, we still ensure that all other variables are still non-negative. Now this is under the condition that all variables must be non-negative. However, if we have a variable that may be unrestricted in sign, it means that the variable may be negative, then this procedure will be affected. What we are going to do here is to handle the unrestricted in sign variable such that we can still do the same simplex procedure. So we will not change the simplex procedure, but instead we are going to do something to change the unrestricted in sign variable or URS variable such that we can handle it as usual. So the idea is that we transform the URS variables such that all variables after the transformation are still required to be non-negative. So here's the idea of the transformation. Let's say the variable x is URS, unrestricted in sign. For example, it means that it can be minus 12, minus 3.14, it can be 0, it can be 0.8, it can be 5, it can be 100.3. Now, the idea of transformation is that we define x, the URS variable, equals to two other variables, which is x prime minus x double prime, in which both of these new variables, they are required to be non-negative. Let's see how this idea works, that we can represent this value using two new variables that both are non-negative. So let's see this example one by one. If the x variable is minus 12, we may represent it with two variables, which is 0 and 12, right? Because 0 minus 12 equals minus 12. And then for minus 3.14, we may represent it as 0 and 3.14. And then 0.8 means 0 and 0.8. 0 means we may represent it with 0 and 0. 5 means we may represent it with x prime equals 5, x double prime equals 0. 100.3 will be represented by 100.3 minus 0. You may say that actually 100.3 may be represented by 101 and then 0.7, right? Because 101 means 0.7 equals 100.3. Yes, this is possible, but you will see later that this will not be the case. One of them will always be 0. I mean, at least one of them may be 0, maybe two of them are 0 if the original x value is 0. Okay, so that's the idea to represent a URS variable, is to use two new variables to represent that, and then using the relation of x equals x prime minus x double prime. Let's see a problem where we may use a URS variable. So in this case, a baker bakes a loaf of bread that requires 5 ounces of flour and 1 package of yeast. So whenever you see the word requires, it must be talking about the constraint. And also at the beginning of the problem, it says has 30 ounces of flour, 5 packages of yeast. This kind of availability also talks about the constraint. Each bread can be sold for 30 cents. So this is related to the objective, we can guess. And then here is the special thing. The baker may purchase additional flour at 4 cents per ounce, or sell the leftover flour at the same price. So if the baker wants to purchase additional flour, it may do so. If it has any flour that is left over, it may also sell that leftover flour at the same price. So formulate the LP problem to maximize the profit, which is revenue minus cost. Okay, so the revenue comes from selling the bread, and then the cost comes from purchasing additional flour, right? So we may say that x1 is the number of loaves of bread baked, and then x2 is the number of ounces by which flour supply is increased. In other words, how many ounces of flour that we purchase, right? Because whenever we purchase 1 ounce of flour, we need to pay 4 cents, and it will cut down our profit. So that's why the sign is negative here. Okay, but then if you look at the flour constraint, at first we have 30 ounces of flour. Our availability of constraint will increase if we buy additional flour, right? So if we buy additional ounces of flour, now the availability of flour that we have equals 30 plus x2, because x2 is the flour that we buy. Now you can notice one thing, that actually you can also sell the flour, right? And it has the same price, 4 cents. So it means that this x2 variable is URS. It means that if x2 is positive, let me give you an illustration. So this is the amount of flour, so this line equals 30 ounces. And then if we spend the money to buy additional flour, it means that x2 is positive, right? We buy the flour, so we will increase the availability of flour that we have. But then, of course, we need to spend money to buy those additional flour. However, if we decide to sell the flour, then x2 has a negative sign, because this is 30 ounces of flour that we have. Then if you sell the flour, of course, the availability of your flour will go down. 30 plus x2, but the x2 itself is negative. That's why the availability of flour will go down. But then from selling flour, you will get the money. So the objective is 30x1 minus 4x2. But if the x2 itself is negative, it means that you are getting money from selling the flour, right? So here you can see why x2 is a URS variable, because x2 may be positive, which means you buy additional flour. X2 may be negative as well, which means that you sell the flour. So which decision will you make in the as the optimal solution? That's what we're going to calculate using the simplex algorithm. So let's see. So once we formulated the problem into a linear programming model, and then we see that x2 is a URS variable, we will transform x2 using this relation. In other words, we will replace all occurrence of x2 with x2 prime minus x2 double prime. So this is the result. And then be careful with the negative sign. So negative 4x2 means negative 4 times x2 prime, negative 4 times minus x2 double prime. So here's the result. And then from here, we will move all variables to the left-hand side. And then as usual, we will convert this into a standard form. And then here's the initial table. And then we will see that we already have a BFS. So we will use the slack variables as the basic variable. And the table is already in a canonical form. So we are ready to perform the simplex algorithm as usual. Okay, so first I would like you to notice that we do not have x2 anymore in this table, right? Because we have replaced x2 with x2 prime and then x2 double prime. So we do not have x2 anymore. Okay, let's perform simplex. As usual, because this problem is a maximization, we pick the variable with the most negative coefficient in row 0 to become the entering variable, which is x1. And then we perform ratio test, pick the smallest one, and then we see that this should be the pivot. And then we perform errors such that the column x1 at this position becomes 1, and then in all other position it becomes 0. For maximization, there is still a negative coefficient, and the most negative is x2 prime. So again, we pick that variable as the entering variable. We perform ratio test, pick the smallest one, and then here this position becomes the pivot, such that in the next table that pivot position should have the value 1, and then all other value in that column must be 0. For the maximization case, this table or this BFS is already optimal. Now you can see that the value of x2 prime is 0 because it is a non-basic variable. And then the value of x2 double prime equals 5. It means that our original x2 variable equals the value of x2 prime, which is 0, minus the value of x2 double prime, which is 5. So x2 in our original problem equals minus 5. In other words, we will sell 5 ounces of flour. And then here x1 equals 5 means that we will produce 5 loaves of bread. And then the revenue from doing that is 170 cents. If you remember at the beginning, I said that this would not happen. If you have a value of x, only one of them will be positive and the other will be 0, or both of them are 0. But you will never have both variables are positive. So here's why. If you look at the tables in the example that we just solved, you see that the column of x2 prime and the column of x2 double prime, they are the negative of each other. So if here it is 1, the column of the other must be minus 1. So any value in one column, and then for the other column, you will see the negative of that. Which means that if one of them becomes a basic variable, like in this case, x2 becomes a basic variable, and it has a positive value, it means that the other one must be a non-basic variable, right? Because if you want to become a basic variable, you have to have this form, the canonical form. Have the value of 1 at one position and all other positions equals 0. When you multiply this with negative 1, it means that the column of the other variable must be negative 1 in that position. And this is not a canonical form. That's why x2 cannot be a basic variable. In other words, x2 prime must be 0. So if one of them becomes a basic variable with a positive value, the other one must be 0. Okay, now let's take a look at the optimal solution of the problem that we just solved in this video. So this is the formulation of the problem. This is the optimal table, and this is the definition of the decision variables. Now here's the statement. In the optimal solution, 5 loaves of bread are baked. There is no flour unused and there is no yeast unused. Is this statement true or false? As usual, I will give you the answer after the pause on the video to give you the time to really think about the answer. The answer is true. So from the optimal solution, we see that x1 equals 5. It means that yes, we bake 5 loaves of bread. And then S1 and S2, they are non-basic variables. It means that we do not have any unused flour. We do not have any unused yeast. Baking 5 loaves of bread requires 25 ounces of flour. But then remember that we sell the leftover of 5 ounces of flour. So that's why we do not have any leftover of flour. So that's how we are handling the URS variable. And then in the next video, we're going to talk about another example, which is the inventory, multi-period inventory problem, where we are going to use the URS variable again to formulate the problem. So see you on the next one. Thank you.